Good day, everyone. I welcome you back to another episode, which is the 15th episode of our physics for SSS2. And today, in this episode, we're going to be dealing with sound waves. Now, for a couple of episodes, we've been dealing with waves, and today we've come to sound waves. So, I implore you to watch this video to the end in order to gain as much as possible. We can demonstrate the production of sound waves by using a tuning fork. Now the tuning fork has two steel prongs which vibrate when struck with a hard rubber, giving some sounds. During the vibration, the prongs of the tuning fork presents a hazy appearance due to their rapid to and fro motion. And if the vibrating prongs are dipped into a beaker of water, the water will be seen to violently vibrate. Also, if you bring a small rubber, like in this diagram, when we bring a small rubber ball suspended by a thread towards the vibrating prong, the ball will be seen to be immediately kicked aside. One property which is not very obvious but is actually true of sound waves is that sound requires a material medium before it can be transmitted. Now in this diagram, we are going to be showing that sound needs a material medium. So in this case, you have a electric bell covered by a bell jar placed on the plate of a vacuum pump. Then the jar is made airtight by applying thick grease around the base of the jar. Then when electrical condition make the bell to ring and produce some sound which is clearly audible. But when the pump is switched on to remove the air, you can see that the sound made gradually reduces. So when the moment comes when there's no air again in the jar, there will be no sound heard because all the air has been evacuated and there's no longer a material medium for the sound waves to be vibrated and to be transmitted. So that shows that sound waves cannot travel in a vacuum unlike light waves. Now this is diagram that shows the production and transmission of light rather sound waves. So you can see we have a tuning fork here, and when this tuning fork vibrates from side to side, there's a displacement of the air molecules close to the prongs of the tuning fork, and so as a result of that we have the the refraction and compression. So in the first diagram we have the compression of the air molecules that are next to the tuning prongs. Then you have after that you have a refraction of the ones that are far away, and so you have compression and refraction in alternative layers. So that is how sound waves are produced. As sound is also a wave, it undergoes reflection, and the special name given to the reflection of sound waves is called echo. An echo is a sound heard after the reflection of sound waves from a plane surface. So in this diagram, you can see that when a ball hits a drum, the sound wave gets to the wall and then they are reflected backwards towards him. So the wall acts as a reflecting surface, and basically when you have the echoes going back and forth, hitting the wall, going back and hitting again, that is called reverberation. It is the perseverance of sound after the source has ceases, after the source of sound has stopped making the sound. So this affects the acoustic properties of an auditorium or hall. So this is called reverberation, and it is reduced by covering the ceilings and walls with soft perforating boards, which can minimize the reflection of sound waves by absorbing them quickly. Now you can also use hanging curtains and some other methods for trying to reduce the effects of reflection of sound. Now this echoing can also be applied in calculating the speed of sound. So basically, as in this diagram, when you stand some distance directly in front of a vertical wall and then you make a sound, maybe you hit an instrument or you clap 2-inch wooden boards sharply and listen for the echo. When you clap repeatedly and adjust the rate of clapping until each next clap coincides with the echo heard from the previous clap, then you can now take the time interval between successive claps, and this time interval will be equal to the time taken for a sound to travel twice the distance for the between you and the wall. So if you take this time, that means you can now say that the time equals the you can be able to use this equation. If you have the time and then you have the distance, you can be able to use this to evaluate the approximate speed of sound in air, and that is around 330 meters per second. Another effect of sound which has a observable effect on on us is the interference of sound. And when two sound waves that are slightly similar in frequency interfere, it results in a process known as beats. Now, these two sound waves, they will be slightly different in their frequencies. For example, when you beat unifolks of nearly equal frequencies and the waves traveling in the same direction, then the resultant amplitude is a result of the adding or subtraction of the amplitude of the initial waves, and this results in what is known as the waxing and waning of the sound. This alteration in sound with time is called beats, and these beats, they have their frequencies called the beat frequency, and beat frequency can be the addition is actually the difference between the frequency of the two initial waves. Now let's talk about the inverse square law of sound waves. Now this inverse square law, it's talking about the intensity and its relationship with the distance from the source of the sound. So the intensity of sound at any point is inversely proportional to the square of the distance of the point from the source of the sound. So what that means is that if you move away from the source of the sound by a particular distance, then the the loudness of that sound, of the sound wave that gets to your ear, will be decreased by the square of that distance. So this is the formula. It is E equals E naught divided by D square, where E naught is the intensity at the source of sound, whereas E is the intensity at the distance from the source, or rather the distance, the particular location of the observer. One characteristic of sound is the pitch, and the pitch of a sound note is the position on the musical scale. It's a characteristic of a note which enables us to differentiate whether it's high or low. So that's why we have the four sections of musical systems, like bass, tenor, alto, soprano. That is the classification based on the ranges of their pitch. Now we can use a particular method to show that the pitch of sound depends on the frequency. For example, if we have a toothed wheel mounted on a stand so that it can rotate freely, and then we'll bring a piece of cardboard against that rotating wheel, as we increase the rate of rotation, or the RPM of that rotating wheel, you see that the cardboard will vibrate even more, and it will produce a note of the frequency, and the frequency will be given by the number of revolutions multiplied by the number of teeth in the wheel divided by the number of seconds. So as the wheel rotates faster, the pitch of the emitted note is observed to be higher and higher. So that shows that the pitch of sound is actually directly proportional to its frequency. Another property of sound which can be talked about is the loudness. Now the loudness of sound is basically also dependent on the amplitude of the sound waves. So as you can recall, we talked about amplitude in the previous episode, and we define it as the maximum displacement of the particles of a medium from their normal or equilibrium position. So the loudness also depends on the mass of air which can be set into vibration. The greater the mass of air set into vibration, the louder will be the sound produced. The third quality of sound waves is the timbre, and this timbre is also known as quality or tone. Now this timbre represents the fact that our musical note is a mixture of different harmonics of the same fundamental frequency, and when these are mixed together, they form different qualities for a particular producer of that sound. And when I say producer of that sound, it could be musical instruments like your trumpet, tambourine. Now the quality of the sound distinguishes it from another um, instruments. For just like when I talk about musical instruments, when you play middle C on a piano, it will have a different quality from middle C on a guitar, and so on and so forth. So the reason for that difference is basically because of the quality or timbre, and the reason for that timbre is dependent on the overtones and the mixtures of or multitudes or multiples of the fundamental frequency. So the quality depends on the overtones. In waves, and as a result, sound waves, there's a concept called resonance, which we'll have to talk about. And basically, resonance has to do with force vibration, which we dealt in the previous episode. What force vibrations means is that the fact that in nature, vibrations tend to taper out because of the resistance due to their motion. Because even sound waves and waves in particular, in general, they they overcome forces when they are being propagated. So that is why when you can't hear a sound when you are too far away from it. So it's because of the fact that that wave has to overcome some resistance along this path, and so it has become its amplitude becomes so reduced that you can't even hear at all. So unless you go close where the energy is still strong. So that is the reason why we have issues nowadays with our transmission and propagation of energies, because of the fact that these waves also have to do work on their way to overcome the resistance and the opposition to their motion in the mediums. And the reason for this, the the consequence of this is that the strength of waves often diminish. But in physics, there's also a system by which you can make that strength to be continue to be strong, and that is by the system of resonance. It's just like when you're talking about electrical and electronic constructions in networking. There's a particular type of equipment that is known as a repeater. Now, a repeater is used in the networking system to strengthen signals. It's when you pass network signals through a repeater, it is a device that strengthens those signals, and when they were supposed to taper off and become weak, it will strengthen them, and they will be received by the client computer. Now, this time around, when we're talking about waves, the resonance is just like the application of repeaters. So it keeps that amplitude of the wave in continuous um, size and prevents decay. So resonance is a phenomenon which occurs whenever a particular body or system is set in oscillation at its own natural frequency. So because of this, it continues to move in just the way it was without stopping. For example, we can talk about this when we look at four balls like this. When we suspend four balls, pendulum bulbs of different lengths carrying a small mass. Now, when you oscillate the pendulum bulb B, you will notice that in a short time the other pendulum will begin to oscillate with small swings, except C which will be oscillating with a larger swing. Now the reason for this is that both pendulum B and C, they are of the same length, and because of this it's easier for them to enter into the same period of motion. So because they have the same period, you know that the period of a pendulum is directly proportional to its length. So because of this, they can easily enter into the same motion, and so they can exhibit resonance. So they begin to resonate, and when B stops, C continues, and when C continues, B stops. But pendulum A and D can easily go out of motion because there's no resonance. One way we can observe the effect of resonance is in acoustic resonance. So in this case, a tuning fork and a burette tube are brought in close contact with each other. Now the tuning fork is vibrated and is held over the top of the tube, while the water filling the tube is slowly run out by means of a tap as shown. So basically, when you open that tap, the water is slowly running out. Then as the level of water is gradually lowered, there is an associated increase in the loudness of sound from the air column of the tube until a certain stage when the sound produced is loudest. So your sound will increase gradually till it gets to a louder sound. Then it will now taper off, and when it tapers off, it will now increase again till it gets to a louder sound, and so on and so forth. Now that point, that level of water at which the sound is loudest, it is that level that consists with the resonance column of the tube. So that means that length is the particular length of the tube that resonates best with that frequency. So that is what resonance is all about. We will round this episode off by talking about the relationship between the frequency of vibration and other properties of a vibrating medium. For example, when we have a string, there is an equation which says that the frequency is proportional to the inverse of the length and the root of the tension of the ratio between the tension and the mass. So that shows that the frequency is inversely proportional to the length, is also directly proportional to the square root of the tension in the string, and is also inversely proportional to the square root of the mass of the string. So when you combine this equation, you have frequency equals to k over L root T over M. So that k is a constant and it depends on the mode of vibration. For example, when the string is vibrating in the fundamental mode of vibration, then that k becomes half, and so on and so forth. To round up this chapter on sound waves, let's try to see if you can do these exercises on the screen. So if you can send the answers as a comment or to the WhatsApp number in the description of this video. Thank you for watching.